In today's lesson, we are going to be looking at dependent and independent events. So this is the last scenario for our simple probability section. And again, it is just another scenario that we may come across. So really our probability in itself is not too different from what we've looked at before. But we're just going to be looking at some different scenarios, which will require a small change in what we have to do. So let's take a look at a little bit of review first. So Jeff has 6 ties in his drawer: solid blue, solid green, solid purple, striped blue, striped green, and striped black. Suppose he removes one tie at random. What is the probability that the tie is blue, solid, or black, striped? B is looking at what is the probability that the tie is striped or blue. And C, are these events mutually exclusive or non-mutually exclusive? And explain. So again, take a second to think over these questions. I'll pause the video to give you a chance to try them on your own, and then we'll come back with the answer. So looking at this question, the probability that the tie is blue or black, blue solid blue or black striped, we have two options, so we need to add those probabilities together. So 1 out of 6 for the solid blue tie plus 1 out of 6 for the black striped tie equals 2 out of 6, or 1/3, or 0.3 repeating, or 33.3%. B, same idea, except we're looking for a striped tie or a blue tie. So the probability of striped is 3 out of 6 plus 2 out of 6 for blue, but we do have to subtract some overlap here because there is a striped blue tie. So we subtract the one overlap, it becomes 4 out of 6, or 2/3, or 0.6 repeating, or 66.6%. Now, are these events mutually exclusive or non-mutually exclusive? A is mutually exclusive. The two events are separate, they don't overlap. There isn't a blue tie that is also black, or there isn't a solid blue tie that is also considered a black striped tie. For part B, it's non-mutually exclusive because there is overlap. You do have a single tie or event or outcome that is both striped and blue. So we did have to remove that overlap, which means it was non-mutually exclusive. The next review, Rebecca rolls a pair of dice. What is the probability of rolling a sum of 7, a sum of 10, or a sum of 12? B asks, what are the odds in favor for part A occurring? And C is asking, what are the odds against for part A? So again, pause the video, take a second to try to do these review questions. So looking at these questions, for A, the probability of rolling a sum of 7, a sum of 10, or a sum of 12. So that or in the question should indicate that we should be adding some probabilities together. So in this case, probability of 7, which is 6 out of 36, plus the probability of rolling a sum of 10, which is 3 out of 36, plus the sum of 12, which is 1 out of 36, gives us a total of 10 possible outcomes over 36. We can reduce that to 5 over 18, or 0.27 repeating, or 27.8%. What are the odds in favor of part A happening? So this one's a little bit different because remember, we're putting the parts or the outcomes of A happening to the outcomes of A not happening, right? So in favor means probability of A occurring to not occurring, or the outcomes where A can occur to the outcomes where A can't occur. So in this case, 10 over 10 to 26, because there are 10 outcomes where the 7, the 10, or the 12 occur, and there are 26 other outcomes where they do not, we can reduce that ratio to 5 to 13. For C, what are the odds against part A happening? Well, we just flip that. Right? So the odds against, we're putting the outcomes that where part A doesn't occur. So we could make it 26 to 10. We already know that it reduces to 13 to 5. Next, we're going to be looking at, are these two events considered mutually exclusive or non-mutually exclusive? So we're going to do our best to try to classify them. So take a second to look over them and think about, are these two events mutually exclusive? Are they separate, or are they non-mutually exclusive? Or could there be overlap between them? So again, take a second, pause the video, and we'll come back with the answers. So coming back to these different events, so the first one, randomly drawing a gray sock and randomly drawing a wool sock, these would be non-mutually exclusive because you could pull a sock that is wool and gray. For B, randomly selecting a student with brown eyes, randomly selecting a student on the honor roll, again non-mutually exclusive because you could have students on the honor roll with brown eyes. C, having an even number of students in class or having an odd number of students in your class. So this is mutually exclusive. You can't have both at the same time. You either have one or the other. For D, rolling a 6 with a die and rolling a prime number with a die. So these are mutually exclusive because 6 is not a prime number. So these two events are separate. E, your birthday falling on a Saturday next year or your birthday falling on a weekend next year. These are not mutually exclusive. They overlap, right? There is overlap or double counting here because it can be Saturday and the weekend. And then finally, the last one, getting an A on the next test and passing the next test. So these can overlap because you can get an A on a test and pass it. These are non-mutually exclusive events. There is overlap. For the last question, in a large sample of families in Canada, it was found that 80% of the husbands and 60% of the wives were employed outside the home. In 53% of the cases, both the husband and wife were employed outside the home. Assume that the sample is representative of the whole population of Canada. What is the probability that A, at least one spouse is employed outside the home, and B, neither spouse is employed outside the home? So again, take a second to think about these questions. Think about what type of events they are. Again, I'd recommend pausing the video and we'll come back with the answer. So coming back to this question, so the probability that at least one spouse is employed outside the home. So we take the probability, or the 80% of husbands, 60% of wives, but then we subtract the overlap, which is that 53% where they're both employed outside the home. So 80 plus 60 minus 53. I put them over 100 to turn it into a fraction. You could have used the percents as on their own as well. And you get 87%. So 80%, there's an 80% chance that at least one spouse is employed outside the home. B was the probability that neither spouse is employed outside the home. Well, we can use the complement here because the probability that at least one spouse is employed plus the probability that neither spouse is employed has to add up to 1. There's no other scenario. Right? Because at least one would be just the husband or just the wife or both just one spouse or just the other or both. So then neither is the complement. So we can do 1 or 100% minus 87 or 0.87 and that gives us 13 or 0.13. So in this lesson, again, we're moving on to independent and dependent events. So this is going to look a little bit different scenarios, so to speak. So for example, Mark has 4 marbles in a bag, 2 yellow, 1 orange, and 1 blue. He reaches into the bag and chooses another one, replaces it, or chooses one, replaces it, and chooses another. So what is the probability that he chooses 2 yellow marbles, one after another? So if we look at this scenario, the first draw, he gets a yellow. The second draw, he also gets a yellow. So first draw, there's option of yellow, yellow, orange, blue. Then off of each individual draw, there's yellow, yellow, orange, blue for all 3 of them because he replaces the marble. So here we can look through, and the probability of yellow, yellow is equal to 4 out of 16 possible events, right? Because there's a total of 16 outcomes. So 4 out of 16, or 0.25, or 25%. Now this situation is considered independent. Is there another way we could have determined this outcome? Is there another way we could have done this and calculated this? There is. And when we look at what we call independent events, and that's events where the occurrence of one event has no effect on the other, if they are independent, the probability of A and B, or A intersect B, is equal to the probability of A times the probability of B. So the key thing here is now we're adding and multiplying some probabilities together. So we're multiplying 2 probabilities together when they're independent. So if we go back up here, if I look at the probability of the first one, the probability of getting a yellow on the first try is 2 out of 4. The probability of getting yellow on the second try is still 2 out of 4. So when I multiply those together, two over 4 times 2 over 4 gives me 4 over 16. So that's how independent events work, or when we're looking for the probability of independent events. And the one thing you're going to be looking for, and we'll touch on it as we go through them, is you're looking for kind of keywords again. So what's a key indicator in these scenarios that tells us that we're dealing with independent events? We can kind of see it here. It's this word and. So when we're looking at events where it's one and another, these are considered independent. Right? And that should be an indicator that we multiply. One event and another. So determine the probability of rolling a prime number and having the spinner land on red. So the key word here is and. One event and another. So this should indicate we are going to be multiplying our 2 probabilities together. So the probability of a prime number and a red, based off of our scenario here. So we're going to take the probability of a prime number multiplied with the probability of red. We have 3 prime numbers, 1, 3, or 1, 2, and 3. So 3 over 6 times 1 possible red out of 4, which gives us 3 over 24, or 1 over 8, or 0.125, or 12.5%. So there's a 12.5% chance of rolling a prime number and spinning a red. Are these events independent? In this case, yes. They are independent, and it's because one outcome does not affect the other. right? What you roll on a die does not affect what you spin on a spinner. So they don't affect each other, so they are independent of each other. So the probability that Allison passes her math test is 0.9 or 90%. The probability that she passes her English test is 0.7. What is the probability that she passes both? So this means the probability of passing math and English. This works out to, again, the probability of math times the probability of English, of passing both of them. Right, passing both means one and the other. So 0.9 multiplied by 0.7 equals 0.63 or 63%. So there's a 63% chance that she will pass both exams or both tests. B, the probability that she passes math but fails English. This one's a little different. So here we're looking for the probability of math and the complement to passing English, which means failing. We do have to do a quick calculation before because we don't know what the probability of failing English is. We can calculate it though, because the probability of failing English is going to be 1 minus the probability of passing it. Right? So using that indirect method, or the idea that not so much indirect, but the idea that all probabilities add up to 1. So 1 minus 0.7 equals 0.3. So there's a 30% chance that she will fail English. So now the probability of passing math multiplied by the probability of failing English, 0.9 or 90% times 0.3 or 30% is 0.27 or 27%. So there's a 27% chance that she will pass math but fail English. What is the probability that she will fail both? So here we're looking for the probability of failing math and English. We need to take the probability of failing math multiplied by the probability of failing English. We do have the probability of failing English. That was 0.3 or 30%, which we calculated earlier in the last part. We don't have the probability of failing math, but we can use the same method that we did previously for English, because both probabilities have to add up to 1. So 1 minus 90% gives us 10% or 0.1. 0.1 times 0.3, 0.03, or 3%. So there's a 3% chance that she will fail both. Next, we're going to look at Mark has 4 marbles in a bag, 2 yellow, 1 orange, and 1 blue. So going back to that example that we looked at previously. He reaches into his bag and chooses 1, doesn't replace it, and chooses another. So what is the probability that he chooses 2 marbles, one after another? So this one is slightly different because this one has the restriction or the characteristic that he does not replace the marble after he takes it. So this changes everything in our second pick, because we can see that depending on what we picked the first time, those options are no longer available in the second time. So we start, let's look at which pathways gives us 2 yellow marbles, one after another. So we have the first one, we have the second one, that's it. There's only 2 pathways that give us the outcome we're looking for. So again, they're not 16 total pathways now. There's 1, 2, 3, 4, 5, 6. There are 12 total. And there are 2 pathways, so the probability of a yellow and a yellow is is now 2 out of 12, or 1 out of 6, or 0.17 or 17%. So even though mathematically it almost looks the same, it's slightly different because of the scenario. And the scenario that changes is because we're not replacing the marble when we put it back. And this is what we would call a dependent event or conditional probability. So events that have different outcomes depending on what has already happened. That's a dependent event. The outcome of one event depends on the other outcome of another event. So mathematically, it might look exactly the same, but there's slight changes. So the probability of A and B, and is again our key word that we're looking for. So the key word is still going to be the same for independent and dependent. The only difference now, when we're looking for the probability of A and B, we still multiply the probability multiplied of A, now multiplied by this notation here. This is basically just saying the condition. So this is basically saying the probability of B given that A occurred. So the probability of event or of B happening given that A occurred. Right? So that means that the probability for B will have changed because of what we did with the first outcome. So if we go back and look how this would vary, the probability of 2 yellows, we look at the first yellow, there's 2 out of 4 options. Now if we look at the second one, so assuming one gets picked, that means there's only 1 yellow left, and there are now 3 possible marbles to choose from because there's one that's taken out. That 1 yellow has been removed. So this becomes 2 out of 12 or the 1 out of 6. So that's how dependent events work. The second outcome is going to change based on the first one. Right? Mathematically, nothing changes. We're still multiplying 2 probabilities together. It's just what or how we calculate the second outcome is going to be a little bit different, right? Because we have to think about how has it changed. So that's where it can get tricky, right? Because it doesn't look like anything's really changed, right? Formula-wise, aside from the notation, essentially we're still multiplying the 2 probabilities, but again, we have to think about how those probabilities have changed, especially the second one. So let's take a look at an example. So in this case, if the Montreal Canadiens have an 80% chance of winning at home and a 60% chance of winning on the road, what is the probability that they win any random game in the season if a random game has a 70% chance of being a home game and a 30% chance of being a road game? So what that might look like might be 10 games left, 7 are at home, 3 are on the road. So what is the probability that they're winning any random game? So there's a couple things we have to think about. This one's a little bit complicated because there's 2 scenarios we have to think about. Let's go through and just highlight some important information. So 1, 80% chance of winning at home, 60% chance of winning on the road, 7% chance that we have a home game, and a 30% chance that we have a road game. So we have to think about, well, how can they win? They can win at home, a home win, or an away win. They could win on the road. So here we have 2 possible scenarios. It could be one or the other. This or should indicate that we have to add. So we're going to add 2 scenarios together. So the probability of winning is going to equal the probability of them playing a home game and winning, plus the probability of them playing an away game and winning. So in this case, the and, home and winning, indicates that we're multiplying. So probability of a home game multiplied by the probability of winning. We want us to be technical, winning, given that they're playing at home, plus the probability of it being an away game multiplied by the probability of them winning, given that it's an away game. Let me just move some of this out of the way. Right, so there's that conditional probability there. Not that we really have to change anything for this one. So in some cases, if we're given the percents, we don't really have to change anything. So the probability of it being a home game is 80%, so 0.8 multiplied by 0.7, because there's a 70% chance of winning. Oops, I have it mapped backwards. 0.7, because there's a 70% chance of it being a home game, multiplied by 0.8, because there's an 80% chance that they're going to win at home, plus 30% or 0.3 multiplied by 0.6. There's a 30% chance it's an away game multiplied by the 6% or the 60% chance of winning that away game. So we have 56% chance plus 18% equals 0.74 or 74%. So there's a 74% chance that any random game is going to be a win for the Canadians. Next example. So Arbor offers juice samples at Costco. The experimental probability that a shopper accepts a sample is 15%. The conditional probability that a customer purchases juice, given they tried the sample, is 20%. Assuming no one purchases juice without sampling it, how many sales should he have if 500 people walk by? So first we want to figure out the probability, because there's a couple of them here. First, accepting a sample is 15%. Then we have that they purchased the juice, given that they tried it, or on the condition that they tried it, is 20% chance. So we want to figure out the probability that they sampled the juice and they purchase it. So we have the probability of them sampling it multiplied by the probability of them purchasing it, given that they sampled it. 0.15 multiplied by 0.20, or 15% times 20%, which is 0.03, or 3% chance. So there's a 3% chance that they will purchase the juice. So if 500 people walk by, 500 people times 3%, or 500 times 0.03 gives us 15. So assuming there will be 15 sales made if 500 people walk by. So next example, determine the probability of dealing a heart followed by a spade from a euchre deck. So euchre is a card game. It only uses 9, 10, ace, queen, or jack, queen, king of each suit. So it's not the entire deck. So what is the probability of selecting a heart followed by a spade? So here we have to look at the probability of getting or drawing a heart multiplied by the probability of drawing a spade, given that you picked a heart with the first one. So the probability of getting a heart, well, if we look at our euchre deck, there are 6 cards out of 24. We're going to multiply that now by how many spades we have, which is also 6, but it's going to be out of 23. Because our probability has changed, or the total number of outcomes have changed because we've taken one card out. Right? We've dealt one card, so that means that there's one less to choose from the 24. So we have 23 total outcomes. So we have 36 over 24 times 23, 552, or this works out to 0.065 or 6.5% chance of dealing a heart, then a spade. So, just some homework questions again that you can take a look at in the textbook that follow up on practicing independent and dependent events. Again, the main thing from this lesson is understanding what the difference is or how to recognize independent and dependent events. So you do have to think about it because you could look at those questions and it might look very similar to the other questions that we did. Again, one of the key words that you're looking for is and, thinking about how one event is connected to another, whether they're independent or whether they're dependent. You're still looking for that and. And then again, you're multiplying now your probabilities, not adding them. So again, just make sure that you go through and you practice this just to become more familiar with the types of questions or the wording of the questions for independent and dependent events.